So did you guys like the centrality measures? They're very nice, aren't they? Very nice and very useful. So these are the kind of analysis that we are going to perform. Okay, so professor, please, the floor is all yours. I think you're muted or something. We cannot listen to you. We cannot hear you.
Okay, are you listening to me?
Yes, yes, we can hear you now.
Okay,
Yes, teacher.
okay, thank you. Okay, today we are going to talk about network models. It's an important topic. Uh, we are going to review the three more important models that mathematicians, physicians, sociologists have discovered. Uh, they are what is called synthetic models or abstract models, and they are very useful. Uh, so let's begin talking about synthetic or artificial networks. As as these are models, they are not real. Models cannot be real. So they are an abstraction. Uh, the most common name in network science for this model is synthetic networks, but it's synonym to artificial networks or abstract networks. Okay, the first thing that it's important to say is at the very beginning of network analysis, there was a widespread lack of data. There was no data. All networks that were studied were abstract networks, mathematical networks, uh, and some of the most brilliant mathematical minds in the field discover different ways to create synthetic network data by defining network models. We are going to review the three most important models in in chronological order. The first one is here in the upper right are two mathematicians, two important mathematicians, Paul Erdos, one of the most important mathematicians of the last century, and Alfred Rangi. They, in 1959, uh, wrote an article about random networks. Random networks. So this is our first model. Later on, here at the left, Duncan Watts, Stephen Strogatz, young people. In 1999, they, in an important article, they propose a new model in contrast to the random model. That is, I guess, the most famous model. It's the small world model. The small world model. And a year later, this okay, these were sociologists, and this is a mathematician, but physicist also. But and 1 year later, this Albert Barabasi and Reka Albert, a woman, they discover a new kind of model, and it's the third model. This is called the scale-free model or preferential model. We're going to talk about. Okay, there are more models today, 2023. There are more models, but these are the most influential models in network science. Okay, let me talk about two reasons why network models are important. The first is explanatory. After you analyze a bunch of real-world networks, you may realize they all seem to have a common property: degree distribution, high clustering, communities, and you ask yourself, how did these properties arise? Okay. Most of the two last models that we're going to see are they were discovered trying to explain properties of real world networks and trying to generate abstract networks that have these real properties. Okay, this is important. How the properties of a network arise? What is the origin of how can you explain that social networks have communities? How can you explain that biological networks have shortest paths? And trying to find an explanation, they 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 propose these models. Okay. Another reason is analysis and testing. You want to generate fake networks that are as similar as possible to real world networks. They must have the same properties, especially the ones that are important for your research.
Professor, Stephanie has a question.
Okay,
Stephanie,
please,
Stephanie,
Stephanie.
Stephanie, are you there? We cannot hear you. Stephanie, you raised your hand.
Teacher, it was a mistake.
Oh, okay.
Okay, okay. Okay, let's begin with random networks. I'm gonna go into a net logo model to show how is a random network. Okay. Look here. I put some nodes. For example, I don't know, 19 nodes. Okay, 19 nodes. They are here. Okay. And what do you think I'm going to do now? Please, someone tell me.
Generate random edges.
Exactly. Generate random edges. It's
Cualquier cosa
important.
le dice Ángel y sin ayuda, mañana conseguir una persona. Gracias.
Oh, somebody has the microphone open. Who is it? Sorry, let me just
Okay.
mute him. Okay, sorry, Barbara.
Okay, it's important. The random part is not in the nodes, it's in the edges. Okay, it could be obvious, but it's important to say it. So random edge, random edge, random edge, and this is a random network. Okay. Okay. So
Professor,
yes.
Professor, sorry, just to ask them. I think by now they already know should mention or comment on how you can generate random edges. I mean, like to produce different types of networks. What do you guys have to say regarding the edges? Because for in this example, how many nodes do you have, Professor?
19.
And
19.
So what type of networks can you generate? I mean, like random networks could you generate by generating random edges? Who can comment on it? Any comment?
Any comment?
I mean, in what way, in what fashion could you generate random edges? on the possibilities. Anybody? Hello? There are so many ways, right? To generate the random edges, don't you think? Are you guys there? Nobody. Are you alive? What's wrong with them? Ivan,
It is just that the question is not immediately trivial. At least that is what I have in my mind.
but if you would try, how would you start? Like by generating just random edges? Just generate a particular random network. How would you do that, Ivan?
I mean, I actually like. I know there are many libraries to generate random numbers, and ultimately the issue boils down to that. But I do not know what to say in terms of how to generate the random numbers themselves. So that is why I decided not to speak because I do
Okay,
not know how that works.
okay, but maybe you're a computer scientist, I know, so you could like, I'm sure you could find a way to a strategy to produce a random network. Freddy,
Maybe you choose from a set of different nodes, one node, with some kind of a random mechanism that choose one node from that set, and well, that select two nodes from that set and generate the edge between those nodes.
Yes, it's the most natural way.
yes, and then you
Randomly, you choose a pair of nodes from these nodes, and you connect them. Yes.
right, Freddy, and then you repeat this, but depending on how many times you do it, you can get different types of networks, right, Freddy?
Exactly. You repeat until I don't know a parameter that says a limit that I don't know, maybe the count of edges or the degree of the network reach some point.
Okay, good.
Yes.
Okay, thank you.
Okay. What is interesting is you could, with this 19 node, you could generate thousands of different networks, okay? But they share common properties. All those networks generated share some properties. We are going to see these properties, okay? That was the idea of Erdos and Renji. When they generate random networks, they discover common properties to all of these random networks, okay? One of the most important property I'm going to show you now. Look, uh, here, 19 nodes. Number of components, how many connected components are? There are 19 isolated nodes, okay? If I add some nodes, okay, the number of components is going to reduce. For example, here, one second. Excuse me, my dogs arrived. Excuse me 1 second.
Meanwhile, the Professor Alfonso comes back. So going back to what Freddy suggested. So depending on how many times you do this, right, Freddy? You could like that determines the distribution, right, of the network.
Yes. I think that in a long time you will finish with a fully connected network.
Exactly. Or you can, if you do it just a few times, then you may have just a sparse network, right, Freddy?
Right.
Okay, thank you.
Okay, I'm back. I'm back.
Okay, Professor.
Let me. Okay, when we began to put edges, they are began to connect. There's gonna be a giant component. This is a look. This is a giant component. It's a subnetwork that has all the nodes connected. And if I add more, this giant component grows. And there's a moment, for example, and there's a moment when all the network becomes connected, okay? Yes? Erdos and Jerry studied when, at what moment, how many edges have one to put on the network for the network to be connected. And they studied mathematically this process. What they discovered, and is very important, is that the nodes in the giant component, when the number of edges is increasing, is not linear. People thought it was linear, but it's not linear. There's a moment when there's a big growth of the number of nodes in the giant component. This is what is called an emergent property. The network suddenly, the giant component of the network, look, the giant component of the network suddenly began to increase rapidly. This emergent property of the giant component of the random network is studied very much. I repeat, it's an example of an emergent property. Another example of an emergent property is when when you have water and, and the temperature goes to 0 degrees, there's a change from liquid to solid, and it's a critical point, and there's a big change, okay? I don't know, Luis Fernando, how you call this phenomena. It's are
When
emergent properties, okay?
yeah, when water becomes ice, is that what liquid of water becomes ice? Is that what you're saying?
Yes.
I don't know. Anybody? How would you call it? I don't remember actually.
Condensation, is it?
Okay, thank you.
I guess it's condensation, but there's a, a very rapid and a very important change in the water, okay? The properties of the water change totally. The water now has other properties because it's solid. So this kind of change is similar. The so this is an important property of a random network. Another important property is the degree distribution of the network. Erdos and Renyi discovered that the distribution of any random network, it's normal distribution, Poisson distribution. I don't know if you know something of normal distribution, okay? So the nodes, the degree of the nodes are distributed more or less evenly, okay? This is another property of, okay?
Which is surprising, right?
It's surprising, yes, because it's random. So this is the distribution is normal. It's a normal distribution. Okay. Let me show you this other model. Here I could build a random network, for example. This is a random network. This is another random network. And here we have the three important measures that we have seen of a network. Look here, average path length. Random networks have short average path length. Look, 2.01. For going from one node to another, the mean path length is 2.01. Another property of random networks, clustering, triangles, okay? Look. A lot of triangles. Okay. And degree distribution, it's normal. Those three properties were discovered by Erdos and Renji. And this is the random network model. I don't know if there's any question. We could say a lot more about this random network, but this is
Yeah.
the most important
Angela,
properties of the random network.
Angela has a question. Angela Cardenas.
Yes.
Angela, go ahead.
Yes, I have a question reference to the global clustering.
Yes.
I mean, the global clustering refers to areas in the network where the nodes are more connected,
Yes.
or
Where the nodes are most
who is
clustered.
the concept?
Where the nodes are most clustered. Angela, let me show you an example to clarify that. I'm gonna shoot another model. Okay.
Great. Yeah, good question.
We're going to see that model in 10-15 minutes, but I'm gonna show you a network. For example, wait a minute. 1 minute. Wait, I'm going to put more nodes. Look, this is another type of network. Look, the clustering is less, 0.074. The cluster of the random network I showed you before was about 0.2. This network has less triangles, is less clustered. It has triangles, but not too much. It is not clear that it has communities. I don't know how many communities, but it's not clear. Okay, so clusters have to be with communities and with triangles. Okay. If I put the random network, look that the clustering is greater. Okay, clustering is a very important concept. It's not so easy to grasp, but it has to be with communities, with clusters. So these are the properties of random networks. Short path lengths, clustering, not too high, but medium clustering, I could say, and normal distribution of normal degree distribution. Okay.
Yes.
Okay, this was the first model.
Daniel has another question or comment. Daniel?
Okay.
Hi. We can tell that the dynamic networks can use this proposal, or like a, um, I forget the word, um, that the degree distribution and global clustering of a random network is short. We can use it to deduce the in a dynamic network what was the it mm, how
I
is
think,
gonna be the next node connected.
oh,
For prediction.
Yes, something like prediction. The next node's connection is como is like the main important thing that we can. Uh,
Okay, yes, yes. Uh, if you have a real network and you are studying this network, and you find, for example, that the clustering, the path length, and the distribution is similar to this, you could use the properties of the random model to
okay,
predict properties of the network. That is the objective of the model.
okay,
Random models have a lot of properties that have been studied for 40 years. The, how is the global clustering? And there are mathematical formulas. So if you are studying a network that has similar properties to a random network, but it's not a random network, but because it's possible, because your network it's for example a social network or a real network. But if you discover similar properties, then you can use this model to do predictions and to for example, if it's a dynamic network, you could predict how it's going to evolve. Yes. So it's important. These models are important because you can do prediction with them. Okay, it's a good question.
thanks, professor. It's clear.
Okay.
yes, because you can like use this I mean, like run all the background or the concepts about random networks to analyze dynamic networks if they have like similar, I mean, some sort of properties. Yeah, because you can consider in the end, like Professor was saying, Professor Alfonso was saying that like social networks, because they happen at random, like it's not like deterministic. You don't know what's gonna happen there. So I think that's a very interesting point that you made.
Yes. Yes. Very interesting. Okay. As a summary of random graphs, I put these happy and sad faces. Uh, I was wrong. I was wrong in what I said 2 minutes ago. A random networks have low clustering. Okay, 0.1, 0.2, it's low clustering. I put sad face. Later we are going to know why it's a sad face. Short paths. It's important when a network have short paths, and random networks have short paths. No hops. Okay, let me see. I forgot to talk about the hops, but no hops. Okay, it's very homogeneous. There is not a node that have a lot of node degrees. So typically random networks have no hops, and that was one reason why these random networks are not very studied today, because today a lot of real networks, not all, but many real networks had hops, and random networks have no hops. So so for example, if you are studying a network and you find hops, you cannot use the random model to study your network. It's clear? Okay. But it have giant component. And this is one of the most, I repeat, this is one of the most studied property of the random networks, the emergent property of the rise of the giant component. Okay, let's go to the next model. The next model is the small world network. It was discovered by Duncan Watson and Stephen Strogatz. They were studying fireflies, luciérnagas, and when they were studying that, they were trying to make networks, and they discovered these small networks when studying fireflies. Uh, the question they try to answer is why high level of clustering and small diameter of real world networks. They studied some important networks and they discovered that the networks had high level clustering and small diameter or small shortest paths. Remember that random networks have low clustering, and they began to wonder how could networks with high clustering and small shortest paths or small diameter could be generated. And they studied that and they discovered a very beautiful way to generate these networks with high level clustering and a small diameter and a small shortest paths. And they call these networks small world networks. Okay. Let me show you a video that explains very clear these small world networks. So I'm gonna put the link in the chat, and Luis Fernando.
Okay. By the way, Manuel, I think he posted a question, Manuel Peña, but the question wasn't answered, was it, Manuel? I think
No, but I think that after the examples, it was clear that it is like that.
Okay, I send the link of the video. It's about 7-8 minutes. It's a very good video that explains the history and what is a small world network. Okay.
Shorter path. I thought we've all heard some variation of this phrase. It's a small world. Often you have some unexpected connection with someone you just meet where you have some friend in common or a relative that just seems like an incredible coincidence. The notion of small world networks tries to quantify this phenomenon. How connected are we all really? To illustrate this, we can play a little game that you can play yourself. The idea is to take yourself, here's me in Portland, Oregon, and to ask, how can I reach some, say, very well-known person? I'll pick our president, Barack Obama, via a network of friends or relatives or people that you know well. So the question is, can I find a path in my social network to Barack Obama, and how long does that path have to be? The question is, how do you start? Who's the first person you go to? Well, I picked my mother, who lives in Los Angeles, because, for one thing, she's a lawyer, and Barack Obama's a lawyer, so there's a connection. Also, my mother actually is a very sociable person. She knows a lot of people, which also helps. So the idea is to pick someone who's connected to your target person and who also maybe has a large circle of friends. So I asked my mother, who do you know who might know Barack Obama or who might know someone who knows Barack Obama? And she thought for a while, and she said, oh, well, maybe my friend Nancy Bekovic, who is the former president of Scripps College in Claremont, California, might have a connection. And it turns out that she went to law school with Hillary Clinton, who of course knows Barack Obama. So amazingly, my connection to Barack Obama only takes 1, 2, 3, 4 hops. I don't think there's anything particularly special about me. I think any of you can pick a famous person in your own country and try and find a relatively short path to that person. Later, after thinking about this some more, I realized that I might even have a shorter path. I thought about my cousin, Matt Dunn, who's a politician in Vermont. He used to be a member of the Vermont state legislature. And it turns out that he knows Senator Patrick Leahy, senator from Vermont, who knows Barack Obama. So there we go with 1, 2, 3 hops. And I was amazed. So you can try this yourself. It's a fun game. And you can realize that it is a rather short path from yourself to probably many well-known people. And the reason that it's short is because of people that you know who might be called hubs in the social network, such as my cousin or my mother. In the 1950s, the social psychologist Stanley Milgram from Harvard tried an experiment to quantify this small world phenomenon. He did the following experiment. Back then, in the days before email, he had a target person, his Boston stockbroker. So he was in Boston at Harvard, and he knew a stockbroker. And then he recruited a group of people he thought would be very far away, socially speaking, from a Boston stockbroker. That is, Nebraskan farmers. So he put an ad in newspapers in Nebraska trying to recruit people for this experiment. Their goal would be to transmit a letter to the Boston stockbroker. They only knew his name and that he was a stockbroker, via people they knew well, that is, people they knew on a first-name basis. And so they were given the letter, they figure out who to give it to, that person then is tasked with trying to give it to someone else, and so on, to create a chain of friends or relatives by which these Nebraskan farmers can get a letter to the target person, the Boston stockbroker, who they don't know. And what Milgram found was that on average, there were approximately what he called 6 degrees of separation. Now that's a well-known phrase now, the idea that we're all separated by 6 degrees. Here's the idea from his one of his articles, that he looked at the number of completed chains and the number of intermediaries needed to reach the target person, and he found that it ranged from about 2 to 10 intermediate acquaintances, and the median was 5, which is where he got the notion of the 6 degrees of separation, that it took 6 hops to get there. So this illustrates the small world property, the idea that a network has relatively few long-distance links, but there are short paths between most pairs of nodes, usually created by hubs. And what's interesting is that it turns out that not only social networks, but many, many other kinds of networks, in fact, most real-world complex networks, seem to have this small world property. In the 1990s, 2 mathematicians, Duncan Watts and Stephen Strogatz, wrote a paper on this phenomenon from a mathematical point of view. It appeared in Nature, the journal Nature, in 1998, Collective Dynamics of Small World Networks. Here's Watts and Strogatz. And this paper was perhaps the trigger that's really started the whole resurgence of study of networks in an interdisciplinary way. Here's the idea. Watts and Strogatz looked at 3 kinds of real-world networks. A network of film actors, where the nodes were individual actors and 2 nodes were linked if the 2 actors appeared in the same movie. They also looked at a very different kind of network, the power grid of the US, where nodes were generators, transformers, substations, and two nodes were linked if they had a transmission line between them. And finally, the network that we saw a picture of the brain of the worm C. elegans, where the nodes are neurons and two nodes were linked if they're connected by a synapse or a gap junction. So is there any reason that these three extremely different kinds of networks should have anything in common? Well, what Watson-Strogatz found was they had this common structure that they called the small world property. To explain that, let's look at a naive guess for what network structure of real-world networks might be. One guess is that they would be very regular. Here I have an abstract picture of a network with our nodes. Here the nodes are arrayed in a circle, and each node is connected to its two nearest neighbors on either side of it. So this node, for example, is connected to this neighbor and to this neighbor. And this node is connected on this side to this neighbor and to this neighbor. And exactly the same kind of connections for every node. So this is called a regular network. And it turns out that this network, if you scale up to many, many nodes, has a very high average distance between nodes. It takes a long time to get via hops from one node to some other random node in the network, but has a high average clustering. That is, this node, for instance, its two neighbors are connected to each other, and its neighbors over here are connected also. So this has a high clustering coefficient. At the other extreme, you might consider a random network. That is, each node has the same number of connections, but they're connected randomly instead of to neighbors. And this kind of network has low average distance between nodes. That is, it doesn't take very long to get via hops from one node to another, but low average clustering. Well, what Watson-Strogatz found for the three real-world networks they studied was that neither of these naive guesses were correct. Here are some results reported in Watson-Strogatz's paper. They report for each of these three networks they looked at, the average distance between pairs of nodes in the given network. So here's what they found for the average distance in these networks. And they compared that with a randomly connected network that has the same number of nodes and links. And you can see that the random average path length, shortest path length, is a little bit lower, but not too much lower. So each one of these has a relatively small random path length for the given number of nodes, or a huge number of nodes in each of these. And then they looked at the clustering coefficients of these networks. And the clustering coefficients in the real world networks were much, much higher than the clustering coefficients in the random network. In summary, if we compare our two extremes, the regular network and the random network, we can see that these so-called small world networks, as defined by Watson-Strogatz, have low average path length and high clustering compared to either of the extremes. And it seems that this middle ground is where most real-world networks lie. That is, small world networks can be defined as having low average distance between nodes, but high clustering.
The global cohort in Wharton's MBA.
Very nice, indeed. Clear?
Shorter path.
So it's a small word. Professor, are you there? You may be muted.
Okay. Okay, do you hear me?
Yes, Professor.
Okay.
Yes.
Are there any questions? Let me show you.
Sorry, Santiago, I'm not so sure
Yes.
I understand it. So Santiago has a question. So is he talking about this? This is from where the Oracle of Bacon comes from?
Yeah, it's something I heard that is like a theory, or right, the idea that you can pick any actor in the world, and it connects through movies to Kevin Bacon, the actor,
Yes.
in 6 Degrees or Less. So I assume that it's based on Small World Network.
Okay.
Yes, yes, indeed.
I think I have a
There's a game in the internet.
yes. I found it here.
There are games in the internet. There's a game called Kevin Bacon. Kevin Bacon, it's not a very good actor, but he's had a lot of friends. So there's a game in the internet when and you play the game trying to find an actor that is very far more than 6 degrees of separation on Kevin Bacon. And the problem is that you cannot find that actor because that network of actors is a small world. So maximum degree of separation is 6. And there's a lot of games about that property. It's a very interesting property. There are books. There is a book that is called 6 Degrees of Separation, and and uh, and there's a lot of research in finding networks, and I guess the most important property that one searches when finding a network, one of the first is this average path length. Because if the average path length is small, then we have a small world network. Okay? Let me show you this. Let me show you this model because it's very interesting. Uh,
Let me stop. Sorry. Listen.
okay, I'm going to.
I guess they don't know who Kevin Bacon is, anyways. They are too young, I think. But anyways.
Okay. Let me show you this. Okay. What you are seeing here is a regular network.
We are not seeing it.
Okay, I'm going to share my screen. Thank you. Let me share my screen. Okay. Are you seeing now my screen?
Yes.
Okay. Okay, what are you seeing here? Let me show you. It's a regular network. Let me show you one thing. Look, how many connections has this node? You can see?
Yes.
4.
4.
4. And this?
Same.
Uh-huh.
4. So this is a regular network. Look, the clustering coefficient of this network is 0.5. It's very high. Okay? And why is 0.5? I'm going to remember, this has 4 neighbors. How many possible connections between these 4? I guess is
4 times 3
6
divided by 2.
possibilities. And of these 6 possibilities of connecting 4 nodes, there are only 3 connected. 1, 2, and 3. Okay, 1, 2, and 3 out of 6 possible. So 3 over 6 is 0.5. Okay, it's okay. This node has high clustering. Okay, but what is the problem? The average path length is big because for going to this node, you have to go right by here. Ta, 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 ta. Long paths. Okay, from here to here, there is long path. Okay. The average path length of this network is 10.88. Okay? Okay? Watson and Strogat, remember in the video, Watson and Strogat want to find networks with high clustering but low average path length. So what was the idea? This network has high clustering. How can I reduce the path length? Okay? And the idea was the following. Look. Look. What are you seeing? What is this?
Generated random.
These are new edges that connect nodes that are far away. So look what happened. We have before 10.88 for the path length, and now what? How many is 6.86? Okay. Okay. If I continue creating these edges that go from one stream to another, look, the average path length is reducing. Okay. But the important thing is, look the graphs here. The average path length reduced very much, but the clustering not too much. So this new network is going to preserve the clustering. It's not going to change very much, but it's going to reduce drastically the average path length. So we're going to have a network, and what you see here are typical the smaller networks that have both properties, high clustering and low average path length. Let me show you this example with 500 nodes, okay? So you can see clearly the difference of what happened here. Okay, 500 nodes. Clustering 0.5. Look, average path length 62.88. Okay. Look. I'm going to start to put edges. Okay. And look, the clustering varies little. This is a horizontal line. The clustering is not affected, but the average path length go to 69. Now it's 20. Let's continue. Here is the number of new connection, of reconnections, 19, 20, 15. I'm going to accelerate a little bit. Okay, that's the idea. Look, guys, a very simple idea. Very simple idea. Here is very clear. I repeat, clustering is not affected when you put these kinds of edges, but the average path length is drastically reduced. So we have the high clustering, we preserve the high clustering, and we make this network have shortest paths. Okay? I don't know if there is any question.
Any comments, questions? It is very clear.
I'm going to let the model run a little bit more. The average path length is in 9. That simple idea, they published the article and they get very famous. This article that Melanie Mitchell is the woman of the video. This article is the most read article in the history of network science.
Right.
The
Yeah,
article when they show this small world.
Professor, I think Stephanie has a very interesting question. She says,
Okay.
she asked whether this applies for any kind of network, like what you were saying that when you were adding, random edges, whether still, you will reduce the path length, the average, and but still the clustering coefficient uh, stays stable somehow.
Okay, that's a very interesting question. If you put more edges to a network, it's obvious that if you put more edges to a network, the average path length is going to be reduced. It's clear? But the great idea was that they began with a network with high clustering. And they discovered something very interesting. That is, the clustering was not affected. But the average path length, yes. For any network that you have, if you put more edges, the average path length is going to be reduced. But what they wanted to show was this, going from here to here. And in the middle, it's the small world. If I go to the model and I stop it and I look what I'm going to do, this, it's a little big, but this is the small world network. This is the small world network. It's too big, but let me reduce a little bit. Less number of nodes, setup. Okay. Look, when you put a lot of, what you're going to have here in the final product, when you put a lot of edges, this is a random network. This is a random network. Okay, there is I don't know, a surprise in the middle. In the middle is the small world. This regular go to a transition to a small world, and this small world go to random. When you put, how many nodes you have to put here? The adequate number. If you put a lot of edges, you convert this to random. And if you got very few edges, you get regular. So small world is between, okay? Here, for example, if this, not much, this is a small world, okay? This is a small world. This is a small world. But if I put more, this is not a small world now. This is random, okay? The line between small world and random is not clearly cut, but that was the idea of Watson struggles. Okay.
Professor, maybe it's important to. Can you go back to the example?
To the model?
Yes.
Okay.
The other window. Yeah, well, you have the model. That just by looking at it, you cannot tell, because they look similar, unless you actually compute these coefficients or these measures, right? Because if you just look at the network, it's hard to tell whether it's a small world, network, regular. Well, regular maybe it's easier, but maybe random, right?
Yes.
So by looking at the network, it's not easy unless you actually do what you were showing, like computing the average path length or the clustering coefficient, right?
Okay, it's not easy, but what can help you to see these two parameters? 2.11, it's a short length. It depends on the network, but when you are satisfied, I mean, when you're satisfied with you preserve the clustering and had short span, you said, I'm going to stop here. I have a small world network. It's the difference is not clear, but what they discovered was a band here. Because look, this is high, this is longest paths and high clustering. Okay, this is short paths and no clustering. In the middle is short paths and high clustering. Okay, so this in the middle has short paths and high clustering. But what is high clustering? This is relative. Depends on the network you're seeing, but short paths high clustering is typical of small worlds networks. Okay, this is the most famous model. It's very, I guess it's very simple. It's a very simple model, but it's a very powerful model. Okay. Okay. Let's continue here. Okay, I'm gonna recapitulate the important result of the article. It was mentioned in the video. This is you increase the randomness, you have the small world. This is what you saw in the graphs. These points are the path lengths, and this is the clustering. Look that there is a point here when the clustering descends rapidly. Okay, so I guess from I don't know, from 0.001 to 0.1, we have this band of a small world. More than 0.1, this is going to become random. And less than 0.01, this is regular. So there's a band here. And this is this graph, it's a very important graph. Okay. That is a small world. I don't know if there's any question.
Any questions, comments?
Okay, if you put in network X, look, there's a command. There's a command in network X is what Strogat's graph with these parameters. Look, this parameter. This is the number of nodes. This is the number of neighbors. 4 is it's in the case of the model we saw, it was 4. It could be 2, it could be 4, it could be 6, but the normal is 4 that gives a clustering of 0.5. And this is the probability that you throw a edge from one node to another opposite node, something like that. If this is higher, the network generates more edges, and if it's lower, and this is the typical shape, of the, and these are the commands of network X of average shortest path length clustering. But let me see this model. Okay, look this here. Now we have happy face here, high clustering, short paths, but there's a sad face, no? As you can see here, not always, because in the video it was mentioned that there are hubs, but not. It's not typical of a small network to have hubs. Let me see this in this model I want to show you. We're going to see these properties in this model. I'm going to reduce a little bit this. Wait a minute. Okay, this is a small world model. Let me show you the properties. Look, average path length of this network, 2.6. Clustering, 0.25. Okay. Not high, but this is high clustering, 0.25. And look the degree distribution. Is like normal distribution, but it's less between random and small world. This the degree distribution of a small world is less is more is less wide. Is less wide because okay. Okay, this is it. Let's see another. This is another. And look, path lengths 2.6, clustering 0.25. So this is typical. No hops, no hops. It's difficult visually to see if there are hops or not, but okay. Let's put it with less. I guess it's okay. Let me put okay. This is a small with network. Oh, look, 1.7 and clustering 0.46. Okay.
Laura asks, if the small world always says the maximum degree is 6.
The maximum degree is 6
Or,
of, the,
yeah, I mean,
of this
that
network.
was a very kind of example, but like in general, like, if, yeah, I think that's an important question maybe to clarify this, Professor. He's asking whether the maximum degree is 6, but or you could say if the average.
For the 6 degrees of separation.
Yes, that's why.
Okay, okay.
Yeah, because of
Uh,
the paper, because the paper was an empirical study, right, Professor?
yes. This is a very good question. The average path length is a measure of a small world, but also another measure of a small world that is more appropriate to the question is the diameter. Okay.
Yes. I think there is a mistake there.
If I put here diameter, it's probably that the diameter of this is 6 or something like that. But let me tell you that the 6 degrees of separation today is not 6. Could be 5, could be 4. 15 years ago, researchers find the degree of separation of the internet and was about 9.5, I guess. 3 or 4 years ago, those researchers made a new measure, and from 9.6 go to 5.2, something like that, because there are more computers, etc. But it's very anti-intuitive that the internet has diameters very like 9 or 10. I don't remember the data, but it's typical. It's typical of Facebook. Facebook has diameter. The diameter of Facebook, not entire Facebook, but a big portion of Facebook could be 8 or 9. So most social networks are are a small world. Okay. I don't know if there is more questions. Okay. What else have we here? Okay, let's go to the third network model. I have two small videos. Let me we are going to see the first video. Okay.
Let me play it.
Here's a picture of typical In this unit, we're going to cover a different aspect of network structure, often called scale-free structure, but more generally known as long-tailed network structure. Here's the idea. Here's a picture of the typical structure of parts of the World Wide Web, where nodes here are web pages and links are links between pages. And you can see that they're directional, that one page links to another page, but not necessarily in reverse. And you can also see that there's hubs in this kind of network, pages that link to many other pages. And there's also hubs that are pages that many other pages link to, like right here. Okay, so let's look at, in contrast, a random network. So this is what a random network might look like if we just randomly threw down a bunch of nodes and put random links between them. So let's look at the degree distribution of these different types of networks. Here's what the degree distribution of a random network looks like. This is a plot where I'm not putting numbers on these, but you can sort of see the shape is this bell curve shape. This is also called a normal distribution or a Gaussian distribution, or to be more exact, this is really what's called a Poisson distribution. But let's not worry about that. Just be aware of the general shape of this. What's interesting about the random network's distribution is that most nodes have the same number of links to them. If we look here in this middle degree, sort of average degree here, most nodes have that degree. There's a small number of nodes that have very low degree, a small number of nodes that have very high degree, and after a certain numbers out here, they quickly go to 0. Now let's contrast that with the degree distribution of the World Wide Web, approximately. So here I've drawn a picture of the degree distribution. Similarly, it has these bars, except the bars here are so narrow that it looks like a solid black mass. But you can think of it as this kind of plot, bar graph. But the bars are really, really narrow and there's a huge number of them. So this distribution looks really different from this distribution. There's a very large number of nodes here that have low degree and a very small number that have high degree. There's also some other interesting things about this shape. If I plot this from, say, 1,000 to 10,000, and suppose I take this little square here, starting at 10,000, and now plot this little part all the way to 100,000, but I'm now going to blow this up to be about the same size as this. So let's do that. So here's the 10,000 to 100,000, and I blew the whole thing up. So what we were seeing before is this little tiny patch over here becomes larger here. This of course is much lower number of nodes than in the previous plot, but I just want you to concentrate on the shape. If we blow up a little part of this, the shape remains the same. Similarly, if I start at 100,000 and plot it all the way out to 1 million, The shape remains the same. This might ring some bells in terms of fractals. When we have a fractal, remember, is something where if you take a small part of it and blow it up, it looks like the whole original object. It's self-similar at all levels. And a power law distribution is, in fact, a fractal object in the same way that we looked at cauliflower and trees and so on. In this sense that if you take a small part of it and blow it up, it has the same shape as the original. So this is also called a scale-free distribution. And the reason is that this idea of scale. At all scales, it looks the same, and so it's called scale-free. Here's the approximate degree distribution of the web. This is empirically what's been reported, that the number of nodes with degree k is proportional to 1 over k squared. This kind of mathematical expression is called a power law because it involves a variable raised to some power. Here we have 1 over k squared, but that's equivalent to k raised to the minus 2 power. If you ever hear the term scale-free distribution, you just know that that's equivalent to a power law distribution. And what's important to know is what that exponent is. So the definition of a scale-free network is a network with a scale-free or power law degree distribution. And we can see that scale-free networks are fractal-like. Here's an abstract scale-free network. It's fractal-like in that you get hubs that have lots of outgoing links or incoming links. And if we scale down here, we see at this level little hubs. At each scale, we can see smaller and smaller hubs that have the same shape as the original network, roughly. So we have self-similarity to some extent in this network. I'm just calling it fractal-like. And that's why it has a power law-like distribution. And I say power law-like because in the real world, networks aren't really scale-free. Just like in the real world, objects aren't really fractals. They're not mathematical fractals. They're approximations to fractals. And the same thing with network degree distributions. I should point out that scale-free networks indeed have the small world property, that is, low average distances between nodes and high clustering. In 1999, Laszlo Barabashi and Reka Albert published a paper in the journal Science called Emergence of Scaling in Random Networks, in which they introduced this idea of scale-free networks to the large audience. And this really, similar to the Watts and Strogatz paper I mentioned before, this paper sparked a huge amount of interest in the nascent field of network science. Barabashi and Albert looked at many different networks, looked at the empirical data, and proposed that scale-free degree distributions are very common in real-world complex networks. Other papers, such as this one by Closet, Shalizi, and Newman, have been a little more skeptical of that claim that the data is power law distributed. So I just want you to be aware that there is some controversy about whether certain networks are actually scale-free or not. Evelyn Fox Keller, a biologist who studies networks, said in 2005, current assessments of the commonality of power laws are probably overestimates. And that's probably true. But in general, what most people do accept is that many real-world networks, most real-world networks probably, have long-tailed degree distributions, where long tail just means that it has this kind of shape, with many nodes having relatively low degree compared to the number of nodes that have high degree. And this is called a tail of a distribution in probability theory, because it kind of looks like a tail. This is sort of the body, and this is the tail. And this is called a long-tailed distribution because this tail keeps going on and on and on. And that is very different from what we call bell curve or normal distributions. Here's a picture of a normal distribution of human height. This is a nice example because people are lined up here by their heights, with the shortest people over here and the tallest people over here. And you can see that most people cluster in the middle. There's a few people who are very short, a few people who are very tall. Most people are average. This normal distribution does not have a long tail. This goes to 0 very quickly on either side. A power law distribution or a long tail distribution does not go to zero. It has a long tail that drops off. And this has some really important implications for real world networks.
Okay, I don't know if there's any question. I'm gonna share my screen. Uh, Luis Fernando, we have 5 or 10 minutes
But
for
yeah, around 5.
5?
We
Okay.
could we could go to maybe 10
Okay,
minutes.
5 minutes more. I guess I let's talk 5 minutes about this new model, a very important model. Let me show you. Are you seeing my screen?
Yes.
Yes.
Okay, I'm gonna run this model. I'm not going to say nothing, and if there are questions, you could tell me. Okay. Okay. I don't know if there are questions. If not, I'm gonna talk a little about this beautiful network. Okay, this is a Barabasi network, a scale-free network, power law network, as was mentioned in the video. Uh, Properties, please. I'm gonna stop. Properties of this network. One very obvious.
It has clusters per cluster.
Okay, hubs, clustered hubs. It's clear the stars. These stars are hubs. The degrees of these nodes are very, very big compared to the others. Look the distribution. Uh, what you see in the video, look here. A lot of nodes with low degree, all these in the border, all these here are here in this bar, okay? And these stars, 2 or 3 stars, are here in the right part. Degree 59. Okay, not 59, but degree 23 here, okay? This is the distribution, okay? What's interesting is that Barabasi gave, in his article, a, a way these networks grow. He explains how they could grow. Look, they began to grow like that. So he and Reka Albert, in the article, talk about how could these networks could be generated. Yes, and that's important because they later it was found that some fractals and some natural processes are always generated like this. Okay. Uh, as it was said in the video, not all networks are scale-free networks. There's a discussion, but let me tell you that there's also a discussion about the small world networks. Yes, not all networks are small world networks. Not all real networks are scale-free networks. Very few real networks are random networks. Today there are more models, but these models are the most important models and they are used very much because the community of network science know a lot about these models, a lot about these models. There's a lot of research, and so they continue to be studied. They continue to be studied. Okay. Uh, okay, guys. 1 minute more. This was an introduction to these three models. I invite you to the web page. There is more information. I invite you to chat GPT, to ask ChatGPT about these models, and you are going to find more properties of these models. I invite you to the tools, to Gephi, to NetworkX, to visualize these networks. We have no more time to talk about the networks. I guess in next Wednesday we could talk a little bit more about these networks, and we are going to talk about diffusion and vulnerability in networks. It's a very practical topic, uh, and we are going to end before going to Semana Santa with diffusion and vulnerability, two of the most important topics in network science. So thank you for your attention, and Luis Fernando, thank
We'll
you.
take a 10-minute break, right? And
Okay.
maybe, yeah, so we'll be back in 10 minutes. So it's 7:30, so 7:40. See you in a few. Daniel, you have a question?
Professor, I have a propose to my group that is the number nine. Start with the project mini project presentation.
Okay, so you want to go first, right? Is that what you're saying?
Yes.
Okay. And Angela?
Uh,
Thanks, Professor.
I mean to say that if my group can continue after, I mean, if my group can see the second group to expose, please.
The second one. Okay, and what is your team number? Angela?
Three. Ah, no, pardon, four.
9 and 4 then. Okay, so we'll see you in a few. Okay, 9 and 4.
Thank you.
Okay. So everybody back? Mm, we're gonna do this very fast. I don't know, Professor, because
Yes.
maybe I was thinking maybe an hour or so. Because this is gonna be different, because they already picked a paper, so it's just kind of it's just presented quickly about the paper, what the paper did, and what they are going to accomplish with this mini project, that is to replicate, to reproduce what they accomplish in the paper. So maybe at the end we have a few minutes to continue with maybe clarify some things regarding this this fractal and self-similar
Okay.
property, the property of self-similarity. Mathematicians, though that's not common, in basic math, but we have a couple of mathematicians. Have you studied fractals in math? It's maybe in topology, or I don't know. I studied that once in, what was it? Functional analysis was called the subject.
Oh, okay. Okay.
Graduate, my master's in math, and I studied fractals in my doctoral thesis. Actually, my doctoral thesis, I applied some of those concepts there. But anyways, so yes, so we're going number 9, number 4, number 8. Okay, so I think to go faster, I'm going to stop the camera, and I'm going to play. Let me see. I'm going to share let's share the whole screen. Let's see. And let's start. So I'll present. That's going to be faster than number 9. And I don't know if there is a way to have a full screen presentation here. I guess not, right, guys?
Yes, Professor.
But I think this would do. Can you tell me if this is okay like that?
Professor, try F11, maybe.
11, okay. No, because this is under. I'm gonna display from the.
How about function F11?
Excuse me, do you hear me?
No,
Hello?
it did not work. Oh,
Yes, we hear you, though you're not loud enough.
Can you hear me now? Better?
Sorry, not you, Daniel. Daniel was asking.
Oh, okay. It was Daniel. Okay.
Professor, you can download the PDF and
Or if you want, we can present, teacher, professor.
also.
I posted them here because I thought it was gonna be faster.
Yes, we can present it if you.
But that would take maybe longer when we switch from one presentation to another. I don't know what's going on. Yeah, it's because maybe I. Let me see. No, it's not fully here, right? Yeah, that's a F11, function 11, but this is the way it shows. But I think that would do, right? And maybe I just scroll it. I think just to go faster. It's because I don't want to, when we switch from one
Yes.
to the other, then it will take time, and I don't want to waste time in the middle.
It shows like that because it is a PDF.
Yes, I know. But anyways, I think I can scroll it. Okay, you can see it, right? It's
Yes.
Yes.
Let's get started then.
Okay, Professor, thank you. Our presentation is about network science in the context of soccer. We are Daniel Alfonso Garavito, Farid Estepa, Nicolás Arias, and me, Daniel Muñoz. Next slide, please, Professor. Thanks. In the problem description, so what we do was reveal the dynamics and spatial organization in football playing. The article addressed the need for a better understanding of the complexity inherent to team and collaborative sports as a soccer. In that cannot be evaluated by analyzing individual skills of each player. So it take to account more the sum of every group of all the group. The article proposes to a team integrated as an integrated system. So we have to take, or we take information from a match from Real Madrid and Barcelona of Spain's National League to simulate the that the paper do. That information was a matrix in that have the passes between each player, and how many passes has made every player to the other in the Real Madrid and in the Barcelona team.
Okay, now regarding to the network science methods, we evaluate for each team the average connectivity degree, the length, the density, the diameter, and the radius. And for each player, and more important, the closeness, the betweenness, and the page rank. The closeness in this case provides a direct measurement on how easy it is to reach a particular player within a team. The betweenness in this case of study provides a measure of the impact of removing that player from the game. As an example, getting a red card or being isolated by the rival's defense. And lastly, the page rank assigns to each player the probability that he will have the ball after some number of passes that has been made by the team. Okay.
Okay, like my partner says, we calculate the closeness, patient, and betweenness about every player of the teams. And then we separate the nodes in two teams, team one and team two. And we show the results of the calculates. We see the page rank in team one, the node 24, has the highest value, like is the player Luka Modric. And the team two, the highest page rank is the node 2, who's supposed to be Sergio Busquets. And
we also make various plots, various analyses. We create and represent the network. This includes some plots that we can put here in the presentation because we don't have enough space, but we also analyze communities of the network, closeness, betweenness. And one of the key results that we find is that we want to use this kind of analysis to also find community structure in the teams, key player identification, and also some kind of sub networks and network density and connectivity analysis. And we also try to reproduce the first plot of the paper that share the key players and the more usual passes in each team. So thank you.
Okay, good timing. Okay, so But you already did the work. Is that what you're saying?
Yes, we already do the replication of the paper.
Okay, that's good, Professor. Any comment?
Okay. Yes. What tools? What software tools did you use for replicating?
The majority of the code is made, all the code is made in, in Python. In the presentation, you can find the link of the Google Colab notebook. We can also
Okay.
share the screen with the notebook.
Oh, perfect.
Okay.
Another question: the data of the players and all the data were obtained from the internet. You don't have to build the networks. All the data were available to you. The
Yes,
networks. Okay.
yes.
Okay. Okay. Yes. Today there are a lot of networks in internet. So 3 4 years ago there was very few networks. Today there are a lot of information. So it is very good to, because one of the most complicated things to do is to build the networks. Okay. So okay, very good.
Very good, very good. Yes, good job. And yeah, by the way, Professor, maybe we can clarify in this moment for everyone. This is very important, like what we call, Professor called it mini project, small project, because you already get used to, get familiar with the networks, and you perform the first analysis, which will be very useful for the the class term project, right, Professor? The big project, let's call it.
Yes, we decided to put these many projects and the articles because it's important that you get used to the tools, uh, and it's a very important thing because it gives you familiarity with the centrality measures and with all that concept that we see in class. You could see it in a practical way when you replicate the article. So it is very important that the mini project is very important.
Okay, thank you. Yeah, very good, very good. I think good job, good job, guys. I think and it's because you are programmers. Let me see this. I just wanted some reactions. I wanted to upload, but I'm just looking at this screen. But anyways, let me see if I can do this on the. No. Oh yeah. Very good. Very good. Okay. Okay. So let's move to team number 4. Angela, Oscar, and Pedro.
Okay, can you? Sorry. Okay, we're gonna start. The article we choose, and we are Oscar Rodriguez, Angela Cárdenas, and myself, Pedro Angreken. And the article we choose is a social network analysis of GMI Islamia, and it is about the application to counter terrorism and intelligence. Next slide, please. Okay, first, we're gonna make a little description of the article, and then we're going to talk about the data science methods and the results we got. This article discusses the social network analysis of the Jima Islamia cell, which is responsible for the 2002 Bali bombings. And this paper provides a framework for intelligence analysis of terrorism, and it's also like it adds also the understanding the communication and structure, and try to predict behaviors and outcomes when used to real time in real time intelligence actually. And the thing is that the social network analysis is like okay, we look for the definition. It's like a mathematical method to connect different dots and make like a map, like a network of complex human groups. And it helps to predict behaviors and making decisions using the network within the network, and try to understand how these group, word the most important players in the network and pretty much predict their behavior. Next slide, please.
So now I am going to speak about the data science method. So the article used the framework of social network analysis without delving into more complex operations to provide a basic initial framework for an intelligence analysis tool. This framework involves seven structural criteria. These are size. So size of a network refers to the total number of nodes within a network or a dataset. This provides a basic understanding of a network's scale. For this project, this measure was limited throughout the network being limited to the actor within the terrorist cell or involved with terrorist activities. So the next is density. This measure quantifies how interconnected a network is. It is described as the average proportion of lines inset with a node in the graph. It measures the proportion of actual age relative to the maximum possible age in a network. The next is degree of connection. This measures the number of direct connections that a node has. This shows the prominence or influence of a node within a network. This criterion allows the measure of the average number of relation each member has with another members of the network. The next is actor level degree centrality. This refers to the accessibility of a node to individuals within a network because it is influenced not only by the network size, but also it is for formation and structure of the network. This metric aids analysts and identifying network leaders, although leadership does necessarily equate holding powers within the relationships or the network itself, but dysfunction. So, and not an individual centrality signifies the critical importance with the network. The next measure is actual level closeness centrality. So, this is a criterion applied to the individuals within a network and describe how close the actor is to others in the network. The next is actor level between centrality. So with this, is another method like the last that measure the individual's activity or ability within a network, measure the ability to control the flow of information within a network. The communication between the terrorists. So, and the last is clusters. The clusters are simply areas of network within a higher density of relation to other areas in the network. So using these set criteria to the data set that we about to exploit value, we conducted the analysis. You
Okay.
can change the slide, please.
Uh, you can hear me?
Yes.
Yes. Okay. Okay. Network data set. In the article during the data recollection, two matrices were organized. The first one is binary and present the relationship between the members of the operation. These are 17 for 17. And the second is a matrix indicating the frequency of or importance of interaction between the members. These no use in the calculations. I don't know. Uh, but along with the article are a YAML file that contains the graphical representation of the first matrix. Okay, in the right is the representation initial matrix graph, and the results. Okay, in the right is the same graph before slide, uh, but processed with Gephi. We processed conceptual is equal that percent in article, hence the results are same. Okay. Entonces, first, Samudra and Iris are the most important central nodes because this Samudra is the biggest pink node and Idris is the here right uh, bottom left green. In, okay, Samudra connect the left clusters, pink and green. And Idris is the commandant operation. Hence, she or he, I don't know, is connected with all group of the right. See, all green. The second conclusion is nodes with minimal interaction played crucial roles because, for example, Mubarak and Rossi in orange color have a few links max 3 bottom position. And Ferry in the top right Altau have 6 links. They three only interacts with calls, only calls between members. And the last result, both central clusters exceed high density. In the left is a one cluster, and the right is another cluster. Yes, is a are difference by color. So easy, please. And
Enough. I think it took you longer than expected, right? You were supposed to be like in 5 minutes. I think it took too long explaining this. But one question, and then I'll give you, I'll allow Professor Alfonso to give his comment. I mean, asking rather. So did you say you plotted this yourselves, right? The network yourselves using Gephi?
Yes, we use Gephi.
Okay, and you perform already some analysis on it.
Yes.
Okay.
Yes, we send the we send the replication with the
Code.
homework.
Okay, yeah, but this is today was just a proposal, but it's very good that you guys already performed some analysis. Professor.
Yes, how was your experience with Gephi? It's easy, it's difficult.
It's easy, easy.
Intuitive?
No. We use video YouTube.
Okay.
But next, the first use is easy.
Okay. Yes.
Yeah,
Okay.
but very good, right? It's good, and the idea is that when of this again of this activity of this homework is that once you perform the analysis, you try to program it in such a way that then for the big project you just change the network and then you perform the same type of analysis, some of this analysis, right, Professor?
Yes, right.
Okay.
That's the idea. Okay, very good. Any comment? Yeah, that's also
Thanks.
Good, very good. Okay, let's move to number 8. Team number 8.
Okay.
I'll let you know when you guys you get to the 5-minute presentation, okay? And then you have to wrap it up in 1 minute or so, okay?
Okay, so good evening. So we are going to present our mini class project that is the title Women in a Global Network of Directors. So next one, please.
Who are you?
Well, we are Stephanie, Freddy, Jorge, and who's speaking, Manuel.
Okay.
We're going to present to you the problem, the network science methods, the network data set that it was identified for the problem and the paper, and the results reported by the investigators. So the article is titled Beyond Fortune 500, Women in a Global Network of Directors. It is presented by those two authors, Anna Stubesco and Michael Gassner from Cornell University and Yale University. We found this data set and an article in cenoro.org that is like a web page for the network science. This was presented in the 8th International Conference of Complex Networks, and the idea for them was to determine the position of women in various boards of directors, because they identified that even though position of women are like occupied by 9 to 13% of all positions in corporate boards, there is uncertainty known about whether the women are being marginalized for men or for even so other women, because there is like a phenomenon called like queen bees, that some women take like the power, let's say, and don't let other women get to there. So they wanted to identify this. And in response to that, they created this network in order to contribute to the understanding of the role played by women in the corporate boards.
Um, the approach method that these authors chose was the construction of a bipartite graph in which the edges links the directors and the boards. You can see in the left that the C represents the boards and P the directors or the person. And then they made one mode projection. Uh, in that way, the directors are connected if they sit together. At last, they made measurements regarding to the path length, diameter, density, closeness, centrality, between the centrality, and clustering coefficient.
The study analyzed a network of 320,000 individuals who make up the boards of directors of 36,000 publicly traded companies in 100 in 195 countries. This information comes from the website of the Financial Times. This is an international business and economics newspaper. These companies are classified into 10 industry sectors and 120 specific industries. And in these papers, only 22% are women, which evidence a female, evidence a female underrepresented on boards of direction. These are.
Those are the results that the authors discover. They shows that well, they clarify about the degree of the network. Principal, this the second network, the one way, the one mode network that pairs the different persons that in different boards. They shows the degree of the network, the betweenness of the network, the closeness and the clustering, differentiating by the male and on the females. It shows that mostly the females works better in that kind of relationships, has better degrees, has better betweenness, and a higher clustering coefficients in some of the cases, especially when the largest component that are the components with board members above 13%.
Very good timing as well. Good, nice, Professor. Any comment? Very nice.
Okay, guys, do you have the data of the networks?
Yes, yes. In the page that we found, they provide the paper with the data set and with the all the definitions. So we have the data.
Okay, this is a huge network.
Yeah.
So I don't know if you bring that to Gephi, I guess is an hour for the network to load.
Yeah, but our idea is to use Network
Okay,
X,
okay,
and the data set is already like what is this? Like polished. So all the field
okay.
they have like 5 fields, but are very, really well defined.
Yes, it's very important to decide the criterion to reduce it. No, it's not just getting away some nodes and some edges, but when you reduce a network, it is very important that when you reduce it, it preserves the properties of the bigger network. Okay, So
Yes,
so it's
yes, yes,
important
yes.
that you think in that aspect. Okay.
Yes,
Okay.
yes. Yeah, this is for everyone. If the network is maybe too big, maybe to process it, then you need to reduce it. And so you need to use some criterion to maybe to select a part of the network, a community or something, I don't know, whatever. But or in general, as Professor said, that try to just keep a part, a subgraph, a subnetwork, but maintaining the general properties of the network. Don't lose the main properties, right? The general properties of the network. Very good. Very
Okay.
nice.
Very good.
Okay,
Very
thanks,
nice.
teachers.
Okay, so we're going to team number one. Number one.
Yes.
Are you guys ready?
Yes, Professor.
There you go.
All right.
Karate Club.
Okay, so we're gonna present Karate Club. It's an API framework for Python for unsupervised learning on graphs. So we're gonna straight into the problem now. Next, please. Thank you. So the main problems the authors try to tackle here has to do with the challenges involving applying machine learning to graphs. So they built a paper out of this topic. So they propose graph embeddings as a method to transform nodes and edges into a vector space of lower dimensionality, preserving the graph structural information. So this is like a method to have a graph and transform it into something that allows to apply machine learning, basically. Yes, there's a lot of frameworks out there, and they wanted to make this an accessible one. So that was the main problem they tried to tackle. And the objectives here, particularly, are into node classification and are into graph classification and community detection. Those are the three main ones. So that's going to be presented by Johan in network science.
Excuse me, and also link prediction, no? Link prediction also.
Oh, yes.
Yes.
Yes, Professor.
Okay.
Okay, so I'm gonna continue about the network science methods. Well, at the beginning, I thought that maybe a graph could be the scale-free network because of we're gonna work with a data set of the users of the social network as a Twitch. We thought that it could be the scale-free network because of the streamers or influencers that can concentrate a lot of the users or followers. And to achieve these goals, there are two tasks. And the first one is the community detections. And there are two kind of algorithms. In the first place, they work with the overlapping, and the second one with the non-overlapping. So we can see some kinds of algorithms for each one of the cases. We have to say that in this paper they work with a lot of methods, with a lot of techniques, but in our case we're gonna focus on some specific algorithms, like for example for the overlapping, for the community detection we're gonna work with the ego splitting, and non-overlapping with the SCD, for example. And then we got the node classifications that we can see. We also can see two different methods or techniques. The first one is the neighborhood based, and the second one is the attribute node embedding techniques. So we also can see the different algorithms for this case. And we gotta remember that the node classification is about this task involves assigning levels or categories to nodes based on certain characters or attributes. So let's go ahead with the data set.
Okay. All right. So our data set here, this paper actually has almost minimum 4 different data set types, but we of course have to scope it to only one, and it's the one named Twitch Egos. So this data set can be kind of seen as a big network contained or built out of sub networks called ego networks, which basically are single networks, sub networks, which are built around a single person, an ego. They call it an ego, meaning a person. So a person has connections, and those connections have their own connections. So the data set is built that way. So it has 100,000 plus undirected graphs, and it contains a binary label, meaning something very important here. The binary classification task here is to predict whether the central gamer, the ego, the person, plays a single game or multiple games. 0 for a single game, 1 for multiple games. That is the binary label data that is being contained here, and that's used. So that data is already granted. So that data is already given. And the idea is, of course, to apply machine learning methods using what we presented before. So, of course, classification here using 80% training, 20% testing, all that. So that's the main thing here. So yeah, we're going to go straight to results here with Laura.
About the results we encounter in the paper, one is the community detection evaluation. Their focus was on assessing community detection algorithms based on their average normalizing mutual information scores across the various data sets. Like no overlapping techniques constantly or the performed overlapping models. The other result is the model is called node embeddings. They found that multiple schools approaches, including Rail or Wallet and Museo, provides a highly effective in creating highly quality node features. The emphasis here lies in the importance of incorporating both neighborhood and attribute information for optimal representations. The other is the Karate Club framework overview. This offers a diverse set of the procedures for community detection, node and whole graphic graph embedding. His contribution extend beyond that, providing accessible graph manning tools and adhering to API-oriented design principles. About the graphs classification tags, they utilize graph representations as a predictors. Performance was measured using mean area under the curve values for downstream classification task. The other is the no classification experiments. They evaluate the performance of node embeddings in predict node levels. They report average area under the curve scores for different embedded techniques. And these techniques can be used for various tasks, social leak prediction and node classification. About the dataset and results, this research for cover diverse datasets, including Reddit tweets, Twitch egos is the one of this we study. The results constantly highlight the predict power of implicit factorization and spectral fingerprinting techniques in general in generating high quality representations.
Okay, enough, I think. Professor, good. Professor, do you have any comments regarding, well,
yes.
Maybe you're going a little bit far on deep learning because that's later in the class, but anyways, Professor, maybe the methods, because this is a lot, and we have just a couple of weeks to do that. Professor.
Yes, the mini project you choose deal with a very important topic that is graph machine learning. Uh, Today is very important. Uh, the purpose of the mini project is to replicate the article. So I guess you could replicate it. You you must use, I guess, machine learning tools and node embedding tools that today are very popular and are very easy to work with. Uh, it's as Luis Fernando said, it's a little ambitious. It has a lot of topics: node classification, graph classification, node embeddings. But because this is only replication, I guess it's viable. It's I think
Yes.
you could do it.
Yeah, but maybe if it is too much, then they could stop in the middle because I think and maybe just focus on some of these as methods, right? Not the whole thing, right? But maybe just some of
Yes.
the methods. Okay, guys, it's not
Okay,
maybe too much. But
that was the question I had because I was about to ask if we could, of course, scope this until certain point.
yes. Just as
Like,
yeah, regarding the time that you guys have, then just focus on just a couple of those methods and then perform
yeah.
some of those analysis, but not the whole thing because that may be too much. Okay.
Okay.
Very good. Very good. I think it's a very nice
Okay,
project.
very good.
Okay, so number 3, get ready. See number 3.
Okay, professors.
Let me see. Let me just post it.
Okay, we're going to work with community structure in jazz. We are Sergio Arguello, Sebastián Campiño, and Valentina Ruiz. The paper of the problem is the name is community structure in jazz. They was work by Pablo Leiser and Leon Danon. Okay, the problem description. The problem is addressed in to understand social interactions and collaborative patterns in the history of jazz music. In the article, they focus on collaboration networks within the context in jazz. They examine two levels of networks, one for musicians and one for the bands, and the connections are if they share musicians. It's important to say that although the idea is to understand the jazz network, the network doesn't allow a chronological reconstruction, as no chronological records are presented within the network. Okay, next, please. They work with the four science network science methods. The first is community structure analysis. They used the algorithm by Girvan and Newman for identify communities. These are based on the centrality of intermediation of the links. And second, they work with collaborative networks. And in this, they explain that the two levels of networks, the network of the musicians and the network of bands. They use the degree distribution for examining finding a power law tail in the musicians. And finally, they use the degree correlations to understand the connection preference between high degree nodes.
Okay. About the network dataset, we obtain it from the Red Hot Jazz Archive. That's a digital database, and we center in two aspects of importance. The first one was like the individuals, so from musicians to another musicians, and the second one was for bands. So, like the relation between two bands that has almost one musician in common, and another relation between bands that don't have it. So, from this include the analysis where 188 bands that performed between 1920 and 1940s, with the majority bands in the 1920s. The database lists the musicians who played in each band, and without discussing which musician played at different times. The bands contain 12 and 75 different names of musicians.
Okay. In the chat, there is a photo about one of the community network graphs. So in that graph, we can see that basically there is a segregation between a racial segregation, like in the right part of the photo, there is a big community, and almost all the musicians in that part of the community are white, and in the left part is the same but with black people. So one of the results of this study is that there is a segregation between the relation between the bands and musicians. Also, we can see that the location is very important. Like,
sorry.
Yeah, no worry. So, for example, in this photo, in that one, okay, there is a relation between the location of the musician. So you can see that in the in the third slide, please, just for a sec. Like,
This
there,
one?
yeah, there is like a relation between the location of the musician. For example, New York are the blue dots, so you can see like there is a branch where the relation of the musicians are mainly New Yorkers or musicians. Also, you can see the same with Chicago, and you can see other relations. So there is a segregation by location too. So basically, also we have another like result, and it's like the distribution is heavily skewed. That indicates that the data is not evenly or uniformly distributed. And you can see like this type of network, social network is similar to sorry, is similar to an email network. So it has a behavior similar like in this graph. And that's all, I guess.
Okay, good. Professor, any comments on this? I think this is also
Okay, thank you. This is a very popular network. It's a network that has to deal with relation with musician and bands. In a sense, it's similar to the collaboration networks of researchers. In the sense that if a musician participates in lots of bands, it's like a researcher that is cited very much of other researchers. There's a similarity, and this is one of the reasons why these data sets are studied in music, in theater, and in other topics. And another important thing is that the data is available. So I guess it's a very appropriate article for replicate.
very
Okay.
good. Yes, I have no.
Thank you, professors.
Okay, good. Let's move to team number Six, please.
6. Can you hear me?
Yes.
Yeah. Okay. Hi, everyone. I want to start because the time is gold. Well, before to start, I want to be with a context about of the article or paper that we to choose. The name is the event that's occurred in Rana Plaza, because in this place was a textile factory in Dhaka, Bangladesh, which killed more than 1,000 factory workers. This was the core for a really big research about of the impact in the social networks. In this analysis was the range of time in 2013 and 2022 about of the combination and tweets and trends about of the quantitative network theory and qualitative discourse theory methods about of the impacts of this collapse. It's important to say that this combination of quantitative and qualitative methods reveals at the final of the results that this course in the social network separated into 3 phases: reporting, reprocessing, and commemorating. In this case, that was very, very sad. The problem. Okay, the problem is about of the discourse around of Rana Plaza disaster remaining larger unexploded. In this case, was several factories commenting about important people, influencers. That was the catastrophe about. The centrality measures identify and classify the most influential entities in complex networks just in this event, but was spread in the social network Twitter in this case. Okay.
We'll continue. We will continue.
Okay, sí.
Who is it?
Yeah.
Who's next?
The methods that the authors use in the paper are matrix function-based centrality measures, community detection, the Lovan community detection method, qualitative analysis by the sociology of knowledge approach to discourse, like Paulo said, and interplay of quantitative and qualitative methods.
It's important to say that the qualitative analysis from the sociology acknowledge in this part of analysis, the selection of tweets considered in the qualitative content analysis is based on centrality measurement. For the qualitative analysis of these tweets was used the sociology discourse of acknowledged approach in this event. That was very sad. In the next method, that is interaction and quantitative and qualitative methods, all the tweets that was analyzed from the union and 10 most central users, and both centrality measures in this time, that was in 2013 and 2022, that was analysis. During the coding process, each core user manually review and aggregating all the tweets that was mentioned in this disaster. Okay.
The data was extracted over a 10-year period from 2013 and 20. A total of 101,103 tweets were gathered. The highest tweet volumes were recorded in 2013 and 2014, and the lowest was observed in 2019.
Okay, it's important in this part about when we try to explain of data sets, it's important to say that we have the information, the paper has all the data
that is important. And in this topic, try to discriminate that fields important to analyze, that is the text, the timestamp, the tweet ID, the user ID. And in the next slide, we can to verify that was the impact in several countries, people, influencer, etc.
Something important to say is that Indonesia shows a remarkable high tweet volume in the year of the collapse, followed by a rapid decline and very low tweeted volumes in subsequent years.
Okay, in this graph, we can to verify very explicitly that the how was mentioned this collapse on this disaster in this occasion. Other thing that is important to say in this case that the detailed of analysis that we have in the data set reveals a strong heterogeneity across in years for conclusions. For example, in the year 2013 was detected three main codes. What we can to say when say the mean the term code. Code is topics that was important in this year. For example, in 2013, the people commented about the number of deaths, news, the standard of safety, for example, in this occasion. In the next year, that is 2014, appearance A codes or A topics that was important to resolve. That is, for example, analyze good practice, wellness histories, the families, and the years 2015 and 2022 in this range, the environment of the social network was around of the similar because the topic that was commented in the social network is around of the publicity and the justice for all the people that was that.
Okay. Okay. Professor, any comment? I just wanted to comment maybe on the methods here. Professor?
Okay, it's an interesting article. I didn't know that these tragedies and these events were analyzed that way by social networks. This postmortem analysis, and it is very interesting. The only question I could have is, I guess it's these are like temporal networks. You're analyzing time series or temporal networks. I don't know if
Yeah, the reason that this research is to be a strong analysis in the line of time. However, we try to explain in a short time to the impact and how to change the comments in several years. But the reason in the deep is the how the 1,000 people how can to have justice across the time.
Okay, this requires not only network science but some knowledge in time series and things like that. So it's interesting to see the intersection of network science with time series and temporal networks. So
Sure.
very good. It's very good that you could do the integration of these knowledge areas. Okay.
Okay.
Yes, I don't know if they actually, include all the tweets and the time is not actually included there, but maybe in the color here or something, because of the measures that they compute here, I don't see anything like time series or something like that, Professor. But rather static network. Maybe the time is implicit there in the network somehow.
It's probable. Yes, I think yes. I think
it's implicit
They
somehow.
use multi-layer network modeling and temporal analysis. This study conducts a temporal analysis of the discourse network over a period of 10 years. By examine the network properties and the community dynamics at different time points. The authors can track the evolution of the discourse, detect change in the network structure, and identify key, key themes and trends over the time. This
So,
temporal analysis provides insight
so
into.
they analyze several networks, and maybe I mean, like a static network at different periods of time, and then they try to make some analysis or some association or some analyze the changes in the network or something like that. Because yeah, if it is time series analysis is going to be more complicated, right, Professor? It's going to be hard.
Yes, but I guess I've just said in the last section, I guess I said that this is typical of this course to that the students include topics that are not seen in the course.
Yes,
Because this network science and data science are very broad. So there are new topics. For example, multi-layer networks. We are not going to see multi-layer networks, but I guess this group is going to research a little bit about that and to replicate the article, and they gonna and they are going to learn things that are not in the themes that we have. So I guess this is a good point of the course.
Yes.
We are learning new things, and the students in the groups are learning topics that are out of what we're going to say. Okay.
Okay, very good, very good. Yes, and maybe if it gets too complicated, let us know. Yes, Professor. Okay, very good. So now we go to team number 6. Sorry, 2. 6. I'm lost. It's 2, right? This is 2, right? This is team number 2.
Yes, teacher.
Sorry, my bad. So team number 2.
Okay. Hello, everybody. Today, our team, Santiago, Sergio, and Laura, are going to talk about the centrality measures applied to the network in a specific case. Next, please. For this, we are going to explain the case study and the problematic, what were the centrality measures applied, and what was the result. Okay, first, we have the question, how can we use the network to solve public health problems? In this case, the problem is tobacco consumption in the United States. Some data reveal that 1 out of every 5 deaths in the United States is due to tobacco. The authors of the research, mapping US government tobacco control leadership network for success, built a social network to help 11 agencies of the Department of Health and Human Service to communicate more effectively in order to reduce tobacco use more quickly. Next, please.
It's my turn. Okay. So these guys are very interesting. Excuse me. You listen to me?
Yes.
Okay, thank you. So this guy is very concerned about the tobacco consumption. The principal strategy is utilizing social network analysis. The DHHS agencies are very connected or very disconnected group of people working about this control on methods in tobacco. So yeah, let me see. Okay, these guys are using this technique because yeah, with surveys that are very interesting in looking for a relation between the people works in these agencies like mails, like messages, and meetings between them, and all of them through the service. So this network is in principle in first place is a directed network, but they applied a technique called symmetrization process for networks that involves converting a directed network into an undirected, ignoring ignoring by direction of connection between the nodes, because this process is useful for simplifying analysis and focusing on the present of relationships. So the focus for them, the approach is the relations. So the directionally which is particularly beneficial studies where the direction is important or useful in interaction, but in this case is less relevant. Um, so about the centrally measures, the principal approach is between the centrality, because between the centrality is mathematical, very useful for find uh, uh, these guys, these agencies, excuse me, these agencies in the network, um, with the very shorter paths. So that's is very useful, because when the agency is a high between centrality, the information is very very quickly between this point. Yeah, it's a bridge, is a very quickly bridge of information. Um, another centrality measures like okay, let me see the next slide, please. Yeah. So the principal centrality measure is between the centrality. So in Gephi software, we calculate maybe automatically. Gephi is very smart, and closeness centrality and agent vector centrality. But this measure is very ignored by the authors. So the focus is on the between centrality, because the closeness centrality and agent vector centrality is not useful at all. For example, closest centrality is about the indicate how quickly information and resource can spread from a given node on the rest of the network. But in this case, there is some gaps in the network information, so this is not clear for them. And an agent vector centrality measure maybe is a good idea, but it's not useful tool for the authors. The metric is particularly useful in networks when certain nodes serve major hubs, seen in scale of free networks. So it's useful for identifying key influencer, or maybe understanding information spread. But in this case, these guys are very interested in the relations. It's very simple analysis. So it's all.
What were the results of the paper?
Okay, our analysis of
Santiago?
do you hear me?
Hello?
Hello? Hello?
Are you listening to me? Are you hear me?
Sergio is speaking now.
Yes, me. I am speaking.
Is it me or?
What do you mean?
Hello. What happened, Professor?
Do you
Okay.
finish? I don't know. I'm
No,
not here. It's my
Yeah.
Do you hear me?
Results is the next slide for my partner.
Yeah, sorry. It's number 2. Sorry.
Hello? Hello? Hello?
Yeah, but
You're not alone, Sergio. I hear you.
Okay.
I don't know. Time is out. What happened? I cannot hear you.
Okay, for this part, in the investigation, we can um, um, see the results. The first one is about the centrality measures. We can see that members belonging to the OES and CDC agencies act as bridge between the other members of the network. And the second is that some agencies, such as FDA and CMS, have a very limited or not connection with the other agencies. With with these two principal results, we can see that it's important to have a better communication between the agencies on the HHAs, and the network analysis provides the need for the greater communication and collaboration on tobacco control across of these agencies.
Okay. And see, I just wanted to see the professor. What is the
Okay,
network data set?
it's an interesting topic, uh, and I guess it's original to investigate effects of smoking not by networks of persons but networks of agencies. No, sometimes the agencies are very important because they made the regulations for the tobacco. So analyzing the relation between the agencies is a very good idea. I guess that these researchers, after seeing relation with the agency, came to see the effects that have on networks of persons, these
Yes.
regulations.
Yeah,
So
but yes.
it's interesting.
Yeah, Professor, but so what is the data set? Because you did not describe it. Is it is this the network? Or is it
Yes,
just a,
they describe the network. They
yeah,
put
I'm talking about the size of the network and the
okay. I guess the size is small because okay, how many agencies? About 20, 25?
We can see this in the last part. Can
Yes.
you move?
Yeah, the last slide.
I here it's about 30 agencies. I don't know if this is
Uh,
in United States. It's in United States, okay?
yes.
these are taken are these taken for the from the paper itself?
No,
This
this
thing.
this is Kefi. This is Kefi.
So you already plotted the network. These are your own drawings of the network, right?
Yeah, yeah.
Yes.
Okay. Yeah,
Please,
that's
please show the last slide. Is the uh, last. Oh, oh, I don't know what happened here.
The network disappears.
Yeah. So I don't know. Yeah, because
Okay.
it was very
Yes.
important to say how
It's a small network. It's manageable for calculating centralities and doing a very good analysis. I guess.
yeah.
Yes, in this network we have 53 nodes and 446 links
Okay.
between the agencies.
Okay. Yeah, it's a small network. Yes.
Here on chat, you have the GitHub project to the dataset.
Okay.
Graph.
Okay.
Okay. Let's move to
Very
because
good.
we're running out of time. Very good. It's good though. The network is kind of small, but anyways, I think still you can perform the analysis. Let's move to team number 7, please.
Okay, can you hear me?
Yes.
Okay.
So you have more tobacco.
Yes, we are going to say it. We select the same paper as the past group, so information is going to be well the same, similar. In the group we are Wilber Lopez, Santiago Rodriguez, y me, Henry Percy. The problem description, according with the authors, the Department of Health in United States has one biggest activity is to protecting the health of Americans. So part of the responsibilities are related with the mitigation control of tobacco. So they established three biggest questions related with. One is communication, where what were the partners of communication between individuals working on tobacco control. Collaboration, what were the patterns of communication between the DHHS agencies working on tobacco control. And three, the challenges, what gaps are or challenges facing the DHHS tobacco control system were revealed by this structural analysis. So if, as the previous group says, we have a key here, a problem of communication between agencies, and the finality of this is control tobacco in the population. So what were the methods used in this case uh, for the network in this case? So they start with one first steps that was identify the agencies related with the DHHS. They identify 11 agencies that from which they try to using a survey get data to analyze or get information over uh, how the communication between agencies works. The next step was the cleaning of the data. They do the cleaning of the data using SPSS, statistical software. Then they construct the network using project. I have been reading about this software. It's quite old, but it's quite nice. And they use this software project, and then they start to develop some statistical analysis. And then with this information, they construct the analysis, the network analysis over density and centrality.
Okay, as we saw, the data from the datasets comes from surveys. And the most important part of the survey is that they start with awareness. So they ask each person if they know of the existence of the others and if they know of their work. And then they select those that know each other and try to measure the frequency in which they communicate with each other. So they ask them how frequently they talk about work or other things, and they measure it in daily, weekly, monthly, quarterly, or yearly. And each of these measures receives a value from 0 to 5. Then, as the other group said, they try to make the networks symmetric, because communication between two people is symmetric. So if one person in one couple says the communication is level 3 and the other person says it's level 5, then they average the communication to 4. And that way they can make a network that is symmetrical and it is undirected. And then they limited the links between the nodes to only the people that had communicated quarterly or less, because they're trying to make it a common communication. Here we have the results, the different networks that they created. These are from the paper. In the left, we have the principal network, in which each node is an individual identified by a number and the agency it is part of, and it is also reflected in the shape and the color of the node. The size of each node is the between and centrality calculated for each node. And the links are obviously the fact that they have communications between them quarterly or less. And we have 55 different nodes, and the density of this network was 0.16, which is not low. However, they also calculated the intra-agency density and the inter-agency density, and they saw that there's a lot of communication inside each agency, but there's little communication with other agencies. So they extrapolated the information to the agencies, and in the graph in the right, we can see that there's a couple of agencies that have huge between the centrality, and others that have little, and these are hubs, which means that all the communication goes through them, which is not ideal because the idea is that every agency can communicate with each other, and this is a problem that they identify and try to solve. And they also identified that there are some agencies that don't have any communication at all with others, like the CMS and the FDA, which is in the bottom. And these are like the gaps they try to identify, and they want to work on in the future. And that's quickly what the paper talks about.
Okay. Okay. Yeah, I think in general for everyone, when you describe the data set, you need to give an idea of how big the network is, because we don't know that in some cases, but in some cases you skip that. Okay, any other additional comment, Professor? I think I don't have any comments. We run out of time.
Yes, we're out of time.
We're missing just one team, which
Yes.
has the situation, by the way.
Is that us?
Yes. Yes, there is the situation with this team. Save it for last. And we run out of time. Yes, remember, and that's where we had a workshop on how to work in a team, and I know that maybe in other teams there may be some issues like that, but in your case is very critical. So that you deliver two versions of the homework. So Alejandro, are you there?
Yes, teacher.
I don't know. I don't know if we can take it maybe a few minutes, please, just to listen to the person, to the problem and the network. Oh, what happened here?
Okay.
I guess you have to all explain what.
Teacher, could you repeat the last part, please?
Okay, guys, I guess that Luis Fernando left the meeting. I don't know if there was a problem with the connection of internet. But Luis Fernando is not. Let's wait a minute if he tries to connect again.
Okay, I will start my presentation.
But there's no slides.
Okay.
Okay. Yes. Go on. Go. Okay.
So I will start to present. So I work in this work that is network science analysis of paper malware universe to look almost like a real social network. So the general problem on this paper is that we have a network about the Marvel characters, but the interesting point is the Marvel Universe collaboration network a similar network to real ones? So for example, we have our networks such as movies, basketball teams, scientific papers, and other ones. And the
Something's going on. What happened? Can you hear me?
Yes.
Yes,
You
teacher.
disconnected.
Am I having a problem?
And now Professor Alfonso left
Hello?
as well.
Hello?
Is it me? Professor? Anybody?
Yes, teacher, we
We can hear
can.
you. Yeah.
Something happened. What
Can you
He
happened?
hear
cannot hear
us?
us.
What's going
Can you
on?
hear? Can you hear us?
Can any
Us.
Spanish
I have,
speak,
I had a connection problem.
please?
I am here.
Okay, just teacher, I was presenting the presentation, so okay, I will continue. So in this case, this paper is
I think
about.
something happened with my mic or something. I'm also connected on my mobile.
Yes, you have a connection
I don't
problem.
know what's going on. Is
For
anybody
1 minute,
presenting?
okay.
Yes, teacher, could you hear me?
Just let me know what's going on because I'm lost.
Okay,
But
I will
nobody's
present.
speaking. Nobody else is. Well, I cannot hear you. So is it me here then? Are you guys speaking? Just let me know.
Manuela Ponte is
Oh,
presenting the
sorry,
slides.
sorry. Okay, just I guess go on, go on. If you have
Okay,
the paper there, just continue, and then I'll just
yes, okay, a brief summary
backlog,
is.
log
Um,
off and log on.
Okay, so the general idea is check if Marvel Universe collaboration is similar to real case networks. So in this case, we have first a character, a character and a relation with a movie, and after that we could model a character with our character relations. So the models in this paper are two. So for first hand, we have bipartite graph, and this is especially useful because we could like map a character to each movie, and that means that each connects a character and a movie, and that has very useful properties. And the good thing about this bipartite graph is that we could model that in a way that we could find the relationship between each one of the characters. So we could create a collaboration network. And other things that this paper talk about is the number of characters, the number of comics, the distribution of characters per book, and the distribution of book per characters, and what are like the frequent heroes in this network. And for our hand, we have like, for example, mean partners per character, network degree, average shorter path, and clustering coefficient. The network looks like that. That is Heroes vertex. That is one part of the network. And for our hand, we have the books vertex or the comics vertex. And the connection between these two entities is the edges, and the edges map the relationship between the character and each one of the books or comics that they appear. And those are the results. And in this table, we compare the current report result against the original paper. So interesting point here is that mostly of the metrics are similar. One thing that is particularly interesting is that, for example, mean distance and medium distance, because this collaboration network was so big, it was a bit difficult to calculate the exactly mean distance. So in this case, I make a sample about 3,500 nodes for calculate the mean distance and the maximum distance. That is very similar to the original ones. And a value that differs very significantly is the clustering coefficient, which is in the original paper is not too big, but in the current report is bigger. And in general, this result shows that even though, for example, the mean distance between each character 2.6 means that there is a high correlation between characters, and is a very probable that different characters or heroes participate together in some of the Marvel comics. And that means that in general, that network could behave similar to real world networks. And our result that this report reproduced was like the principal plots. And for the first plot is the distribution of characters per comic in the bipartite graph. And we could see that the plots are very similar, and the same with the second graph, that is the distribution of books per character in the bipartite graph. in which, in general, we could see that mostly of a concentration or density is around, for example, the first numbers. But for example, if a character appears many times in a book, that is less probable. So in general, that's the result of this work. So thank you.
Okay, Manuel, very interesting article. These networks are very popular. Networks of comics, networks of series like Netflix series. They are very useful for example, predicting which characters are going they in the future to be in the series according to how they interact. I guess you has done the analysis yet, or
Yeah, the
okay.
analysis is that part.
This is from the paper or from what you have done.
Is both. The
Okay.
second column
Oh,
is the
okay.
original paper, and the
Okay.
second one is this report.
Okay. Okay. Luis Fernando.
Yes, I'm back. I don't know, something happened. It froze the computer or something. Anyways, I think, yeah, I got the last part, and I think I think we, as I recall, I don't remember if last year somebody analyzed this same network. Do you remember something about it?
Yes.
Yeah. So yeah, that's another interesting work, and I think I don't have any comments regarding the network, because, but maybe though it's in the context of comics, as you mentioned, it can, whatever analysis you perform there is can be extended or performed on a different social networks,
Okay.
right?
Yeah, exactly. It's quite similar to real networks.
Yes. Yeah, I think we can stop here, right, Professor? Because we keep you too
Yes.
late, and then we have to discuss something with this team, right? I emailed you guys about this, and we need to meet as soon as possible. Please.
Yeah, Professor. But the thing is, we also have we have the presentation as well ready. So we don't know, but the work is done. So if you decide, we can present for the next class. But for sure, we.
No, in the meeting that we are going to have with you guys.
Okay. Oh, okay. Perfect.
Yeah, because that's not what we expected. We did not expect that you had like separate work. Like you are a team all together, right? Like,
Yeah, well, I did not expect that either, and it was not my call. So, does it work for you two professors tomorrow?
yeah, I think let's stop the session here for everyone, and then if we have a minute, then we can maybe agree on a time tomorrow to meet tomorrow. Okay.
Okay.
Okay. Let me just stop the recording. I'm sorry.
Hey, good night to all of you.
Good
Bye-bye.
night, everyone.